Welcome to this comprehensive lecture on endocrinology. Today, we're going to explore a truly fascinating and vital topic, hormone transport. We will discover exactly how these crucial chemical messengers travel through the bloodstream to reach their target cells, and why this journey is much more complex than it initially seems. Let us dive in. To understand how hormones travel, let us imagine a bustling city with a massive, fast-flowing river running right through the middle of it. This river represents your bloodstream, and the urgent messages are the hormones. Some messengers, like insulin or adrenaline, are water-soluble. They are perfectly fine swimming in this watery environment. However, steroid and thyroid hormones are fat-soluble. They absolutely hate water. If dropped directly into the blood, they would clump together and sink, never reaching their destination. Since fat-soluble hormones cannot travel alone, the body has devised a brilliant physiological solution. It provides tiny molecular boats called carrier proteins, which are synthesized by the liver. These proteins safely ferry the fat-soluble hormones through the watery blood. When a hormone is attached to this protein, it is called a bound hormone. The tiny fraction traveling without a carrier is the free hormone. Crucially, only the free hormone is biologically active and capable of triggering a response in target cells. You might wonder why the body goes through all this trouble instead of just making all hormones water-soluble. Carrier proteins serve three absolutely vital functions that keep you healthy. First, they increase solubility, preventing dangerous fat emboli in your blood vessels. Second, they act as a massive circulating reservoir, ready to release active hormones exactly when needed. Third, they protect hormones from being immediately destroyed by the kidneys or liver, extending their lifespan in the blood from mere minutes to nearly a week. Now that we understand what carrier proteins do conceptually, let us look at the mathematics governing their behavior in the blood. This is the law of mass action. Ka is the association constant, measuring how strongly the hormone sticks to the protein. Hp represents the bound hormone-protein complex. H is the free hormone, and P is the free carrier protein. This formula tells us that bound hormone is directly proportional to available free hormone and protein. If the body produces more free protein, the equation shifts to create more bound complex. Before we move on, let us see this formula in action with a concrete clinical example. Suppose we have a steroid hormone with an association constant of 10 to the power of 7 and a free protein concentration of 10 to the power of -6. We want to find the ratio of bound to free hormone. We rearrange our formula to isolate this ratio, then multiply the two given values. The result is 10, meaning for every one free molecule, 10 are safely bound in storage. Now that we have used this rearranged formula to solve a problem, let us understand exactly where it comes from mathematically. We start with the standard law of mass action equation. Our goal is to isolate the ratio of bound hormone to free hormone on one side. By applying basic algebra and multiplying both sides of the equation by the free protein concentration, we perfectly isolate the ratio. This simple derivation is incredibly powerful for clinical diagnostics and understanding hormone reserves. This brings us to a crucial clinical concept: total hormone. Total hormone is simply the sum of the free, active hormone and the bound, inactive hormone circulating in the blood. To see why this distinction matters so much, let us explore a fascinating real-world scenario involving pregnancy. During pregnancy, high estrogen levels cause the liver to produce double the normal amount of carrier proteins. Let us see exactly how this massive increase impacts the hormone levels in a patient's blood. To analyze the pregnancy scenario accurately, we need to formalize the relationship we just discussed into a simple equation. The total hormone concentration is equal to the free hormone plus the bound hormone complex. The free hormone represents the tiny, biologically active fraction, while the bound complex represents the large, inactive storage pool. This equation is fundamental because if the storage pool increases significantly, the total hormone will rise dramatically, even if the active free hormone remains perfectly constant to keep the patient healthy. Understanding this formula prevents doctors from making serious diagnostic errors when looking at lab results. Let us calculate the baseline hormone levels before the pregnancy changes take effect. We are given an association constant of 10 to the power of 9, a strictly controlled free hormone level of 20 picomolar, and an initial protein level of 100 nanomolar. We must convert these units to standard molarity and then plug them into our rearranged mass action formula. Multiplying these values together gives us an initial bound hormone concentration of 2 nanomolar, establishing our baseline state. Now, let us see what happens when the pregnancy estrogens double the carrier protein concentration in the blood. The free protein is now 200 nanomolar. The body's feedback loops work hard to keep the free hormone strictly at 20 picomolar. Using the exact same formula with our new, higher protein value, we calculate that the new bound hormone concentration is 4 nanomolar. The bound storage pool has exactly doubled to accommodate the extra carrier proteins produced by the liver. So, we have proven that the bound hormone doubles. This brings us to a critical clinical insight regarding the patient. Initially, the total hormone was about 2.02 nanomolar. After the proteins doubled, the total hormone became 4.02 nanomolar. If a doctor only measured total hormone, they might mistakenly diagnose a toxic thyroid condition. However, because the free, active hormone remained perfectly normal, the patient is completely healthy, proving why understanding transport is vital. To solidify everything we have discussed, let us look at a visual representation of this entire process. Here, we see the bloodstream, depicted as a vessel. Notice the water-soluble hormones floating freely in the plasma. In contrast, the red, fat-soluble hormones are attached to blue carrier proteins, acting as a massive reservoir. Only the free, unbound hormones are able to exit the bloodstream and bind to the Y-shaped receptors on the target cell at the bottom, triggering the physiological response. We have covered a lot of ground today. Let us summarize the most important ideas. First, carrier proteins are essential vehicles that transport fat-soluble hormones, extending their lifespan and creating a ready-to-use reservoir. Second, the balance between bound and free hormone is strictly governed by the law of mass action. Finally, understanding this balance is the ultimate key to correctly interpreting clinical lab results. You now have a solid foundation in hormone transport.